our webinar about securing web applications with fuzzing. So in this webinar, we will talk about how fuzzing or feedback-based fuzzing or modern fuzzing can help you to secure and find vulnerabilities in your the web applications. So a few words about myself. I am Khaled, one of the co-founders of Uncaught Intelligence. And yeah, so vulnerability detection and binary code analysis have been my passion before. And yeah, at Code Intelligence, I work with our amazing team to develop our core fuzzing technologies and also responsible for our open source initiative. And yeah, you can find me on Twitter, and here also is my email address. Yeah, so before going deeper into the topic, so why should we care at all? So recently, most or many companies are moving into a software as a service model, pushing more of the services into the cloud. And while this has a lot of advantages, it also comes with a significant security risk, because now the web services are running in the cloud, and yeah, any bug and security vulnerability there means that it's not you hack you errors affect one or single users. With these vulnerabilities, basically all users are affected. And we see that critical vulnerabilities or critical OS vulnerabilities, such as SQL injection, cross-site scripting, and remote execution, are appearing continuously in modern software. And with the increasing complexity of modern web applications or web services, so as it increases the need to have an automated way to find these vulnerabilities. And ideally, what we want to have is that we want to find vulnerabilities as early as possible in the development process, because at each stage of the development, the cost of a bug or a vulnerability becomes significantly increasing. And there is the so-called rule of 10, is that at each step of the development, the cost of a vulnerability would be 10 times. And so what we would like to have as a developer, and our vision is that to shift the stages where we find vulnerabilities further to the left, so that we find them at development, at the development or system or unit testing, and with system testing. So with these two aspects, where we can focus on testing like specific modules or the system as a whole, this is the part where we should invest the most effort to find vulnerabilities, because otherwise it will become really costly and really expensive having vulnerabilities at later stages. So before we just get into how we do that and how this happens, I'll just like to give a brief overview about fuzzing. So what fuzzing is, and how it can help to find vulnerabilities. And then we focus more on how to tackle finding vulnerabilities on the unit level and on the system level. So the overall idea of fuzzing is actually pretty simple. So I have an application, I have a software that I would like to test, and I have a fuzzer that just throws some random inputs on the system, hoping that it can find an input that crashes the application. So this is how fuzzing has started over 30 years ago. And yeah, initially it found some vulnerabilities, or several vulnerabilities in the Unix utilities. But you can quickly see that this approach has two main drawbacks. First, and not all bugs can necessarily lead to crashing the system. If we think about SQL injections or remote code execution, they don't crash the system, but these are sort of the nasty bugs or the critical bugs that you would like to find. And the second problem is that this process being completely black box, the fuzzer does not have any information about what's happening inside the application. So you, and especially if the application expects some sort of structured inputs, then the fuzzer would not be able to, by being completely black box, to provide this. And as a try to improve the situation, one thought about, okay, let's, instead of just completely randomly generate the input, let's just start with some examples for the fuzzer, and then the fuzzer can then just perform some mutations based on that. So if we take our image parser as an example, and we just provide the idea would be is to provide the fuzzer with some images as a starting point, and these images, they can come from maybe from your unit test, and the fuzzer would then just try to mutate to change some things in the image, and flipping some bits and changing some bytes, and hoping to just get more code coverage. But if we take a look at this approach, it's just a minor improvement to just being completely random. And yeah, so it basically suffers from the same disadvantages. And so the real breakthrough of fuzzing came with the idea of coverage, or the idea of feedback-based fuzzing. And what does that mean is that we take our example of an image parser, we instrument the system under test, and this means that we just inject some markers in the code, so in the bytecode or in the binary code, and these markers give the fuzzer feedback about which code has been covered, about some interesting values that have been compared against, and with this feedback, the fuzzer can just see if it made progress while fuzzing. So if we take this this example, the fuzzer would just start with an empty input, and what it gets from the instrumentation is something like this. So this is example showing some Java code, and we see that, of course, it's an invalid input. So all statements all if statements are basically false, and so this green annotation here means that the fuzzing feedback says that these code areas have been actually executed. So we see all the if statement, but not the bodies. And obviously this is an invalid image, but interestingly, so what the fuzzer also gets is that the input that it provides has been compared against some magic or some constants. And this is valuable information for the fuzzer, because one of the sort of intelligent mutation that it does is just try to use one of these constants. And when doing so, we see that we were able to trigger new code that was not able to be triggered before. So meaning that now the fuzzer would see, okay, with this mutation, now I was able to reach new code that I was not able to reach before. So meaning that this input was really interesting, and the fuzzer would just, in this case, was able to convince the application to interpret the input as a valid JPEG image, basically. And this way, with this loop, this feedback loop, the fuzzer would then just step by step learn how the inputs should be structured in order to reach good code coverage or to trigger interesting program behavior. And with that, it step by step explore the program state. So this is and the fuzzer does not basically get bored. It just tries several hundreds of thousands of executions per second to explore the program. And yeah, so this is the high-level idea of feedback-based fuzzing, and it's currently sort of the main testing method that are used to find bugs by the big players, I would see, as you would see. So from a developer perspective, how this compared to testing or to your, so with normal unit testing, we just, if I have an API that I would like, or a method that I would like to test, just in my test, I just call this API with some predefined inputs. And the difference with fuzzing is that the fuzzer would come up with these interesting inputs that triggers interesting program behaviors. And also what we usually do with the fuzzer is that we also add more runtime bug detection capabilities that tells us if something bad has happened. And just to give an idea how effective fuzzing actually is, so this shows there's some rather older statistics about the number of bugs that fuzzing has found in these well-known projects. So fuzzing was able to find over 29,000 bugs in Google Chrome alone. And this shows, regardless how good sort of the software is and how good the engineers that are working on this software are, people or humans tend to forget some corner cases, and this is where automated testing approaches like fuzzing are really effective. So we mentioned that we would like to move the burden or the finding of bugs. We want to find the most bugs as early as possible in the development process, and fuzzing is very suitable approach to enable us to achieve that, because first the inputs are automatically generated. So the fuzzer generates input that maximizes code coverage. It has no false positives, because being a dynamic analysis approach, with each finding or with each bug that the fuzzer reports, we get a sort of a reproducing example. We get a concrete input that with it you can trigger this bug, and this is hugely different from a static analysis, where we just get here this might be something wrong, but you have to verify it yourself. Here you get a proof, a concrete example how to trigger these vulnerabilities. It's highly parallelizable, meaning that you can just start many instances of the fuzzer, and this compile time instrumentation, this feedback that we instrument into the code, has a huge improvement of fuzzing effectiveness, as we will see also in some practical example. So you have your sort of a competitive advantage of over attackers that are trying to basically attack you because they don't have access to the source code. And so let's see now, see how can we apply a unit level fuzzing. So fuzzing on the unit levels, because if I have a complex application, a complex web application, so what I would like to have is I'd like to have tests on a unit level that test specific modules, just to know that there are nothing wrong here. And I would like to be able to fuzz the whole system in a sort of in a system test, just to make sure that the interaction between these components are safe and they don't lead to bugs. So we'll start with unit level fuzzing, basically testing special or specific methods in my application. And here we will take Java as an example. So Java is widely used for developing web services, and yeah, for that we'll just start with the unit level. And the tool we'll be using for that is called Jazzer. And Jazzer is a feedback-based fuzzer, or a coverage-guided fuzzer, developed by Code Intelligence. It's in process. This means that the code that you want to test and the JVM basically runs in the same process with the fuzzer. And that's why it's very fast. It can achieve up to or over 1 million executions per second on an empty target. It performs instrumentation on the bytecode. This means you don't need the source code. All you need is your jar files or bytecode, basically, and this enables you to test any language that basically runs on the JVM, like Kotlin and Java. It's agent-based, that the code is instrumented on demand when it's loaded into the JVM, and it's completely open source. So we open sourced this on February last year, and yeah, Jazzer is, and here's the GitHub repo, and it's integrated now in Google's OSS Fuzz. So OSS Fuzz is a service provided by Google to continuously test important open source libraries, and Jazzer Fuzz is the so powers the fuzzing of Java projects there. So what do I need to do in order to write a fuzz test for Jazzer? So on the unit level fuzzing, as a developer, we usually write unit tests for our code. In the context of fuzzing, we need to write what's called a fuzz test or a fuzz target. And a fuzz test is a method, is a just class that has a static method which is called fuzzer test one input, and this method has several signatures. One of them, it takes a byte array. And so and here inside this method, I just call the code that I would like to fuzz. And you can think of this as the fuzzer that would Jazzer would then just call this method in an endless loop, and each time it will provide an input, and it prioritized inputs that sort of say trigger interesting behavior in the program. And yeah, so then you can compile it and then run it with Jazzer. So let's have a look at an example here. So here is an example fuzz test where we just define this static method, and what we do is that we just interpret the fuzzing method, fuzzing input as a string, and we just check if this string of our input actually starts with the string "Welcome to Awesome Fuzzing," and it's more than 30 character, and if the 26th character is an exclamation mark. So just these checks need to be there, and if we pass all these checks, we just throw an exception. And this just to simulate the fact that yeah, an error has happened here. And obviously a black box fuzzer would just not be able by a chance generate as an input that actually matches these criteria. But with coverage guided fuzzing, this is really easy to find because we see exactly that our input is being compared against this string. So all I have to do is I have to just combine my code. And now I can start this with Jazzer. So I just define Jazzer, give it the class path here, and give with one argument which class actually contains my tests. And if I do that, Jazzer would start. It would load the code into the JVM, and we see that just pretty quickly we were able to trigger this exception saying we got there. And here we see the exact input that actually leads to this to this bug, and it's exactly the input that matches all these criteria. And it took just a few seconds to find that, while a black box fuzzer would just, it would not be possible. But of course, we can make it a bit more challenging for the fuzzer. How about this example? So with this example, what we do is we take the fuzzing inputs, we encode sort of the first 6 characters as base 64, and this has to be this concrete value. If this is passes, we just take from the fuzzing inputs 2 longs, we XOR these 2 longs, these 2 numbers, with this our insecure encrypt method with a constant key, and so the results should be these constants, and if all these checks are fulfilled, then we will just throw this exception saying we got there. And obviously here we have a more involved example because we have encoding, we have XORing, and this is pretty difficult to just to come up with it by a chance. And here, just to show this example here, so basically this is the code that you want to fuzz, and as mentioned, we just need to compile it once, and when it's compiled, we can just start it with just also this value profile facet, and all these examples are available into the Jezza repos. So now if we start this, we see that it will take a bit more time because this is not a simple, not only a simple a string compare, but it will eventually find the bugs. And here we see we got the progress that we are finding more interesting inputs, because each time we found an input, we get this counter here increased. And and so one idea as to why fuzzing also good for an integration into the development process is that any interesting inputs that the fuzzer finds, it just keeps in what we call a seed corpus of interesting inputs. And this means that the fuzzer would not start from scratch each time, but it starts from the accumulated knowledge that it has gathered over time. And here we see that we were able to trigger the bug, and the input that triggered this bug is called Jezza value profiling. And just to demonstrate the feature or the technique that we use to crack these kind of inputs. Yeah. Maybe some also more real world examples how with some real world software that we tested with Jezza. So here we see this example of a function called read folly, and here we see that we have this read function or read method, and we just have a loop. Then while having read less byte than we want to read, we just try to read more bytes. And yes, so where it could here be a bug, it turned out that the read method, if there is nothing more to read, it just returns 0. Meaning that in this case, if we have less value to read than we specified in the read folly method, we just end up in an endless loop. And this is a CVE that Jezza found in Apache PDF box. This means that you can just, if you use this in your web service, one can just upload a PDF file, leading to basically a denial of service attack, because your service will then, or the library that you use for that, will end up in an endless loop. And this is the fuzz test that we had to write in order to find this bug. We just called the load PDF method with the fuzzing input, and we just ignore all exceptions. And this with this few lines of code, it was enough to find the CVE. Another more example, this is the library called JSON Sanitizer, which is developed by OWASP. And the idea there is that you can take your input, sanitize it to the library, and then you can, the claim is that you can just copy paste this in your script tag in your HTML file. And because the library promises that the sanitized string will never contain these strings that would enable a cross-site scripting attacks. So, okay, what we did, we wanted to test this claim. We written a simple fuzz test that we used to basically sanitize the input to the JSON sanitizer, and at the end we just checked does the valid JSON or does the sanitized JSON contain this substring. And this shows how you can use fuzzing, because fuzzer is really good in exploring or finding corner cases. And it turns out that, and this is again an example that you find in the Jezza repo. And yeah, basically you can we found the Jezza found an input that after being sanitized still contains the this script tag, meaning that even if you use this library in your web application, your application was vulnerable to cross-site scripting. But this is a CVE that has been fixed now. Yeah, so I hope that by now I was able to convince you that fuzzing is really good, is really effective in finding bugs in the software, is really good in finding corner cases, and even can crack difficult checks. But you know, while it's really good to do this on the unit level fuzzing, because this would enable you to guarantee that the modules that you use are fuzzed, are tested, are secure. How about testing the system as a whole? Because usually in many cases you cannot run your whole system in one process, and there are several challenges how to use fuzzing in these scenarios. And so just to address these challenges, or to just demonstrate the different challenges that when wanting to use fuzzing in the context of web applications. So let's have a look at this example. And this example here shows a code snippet from our WebGoat project. And so WebGoat is a project that's written in Java. It's a Spring Boot application where it has a lot of security vulnerabilities. So it's deliberately insecure to basically raise awareness and to teach people or interesting people about web security and about the different vulnerabilities that you can find here. And we see here from the code snippet that it's a REST controller, and we see the endpoints, the corresponding endpoints, and also from the signature of the login method, we see, or we can see the structure of the inputs that's expected by this endpoint. So, and this is the first challenge of testing web applications or web services on the system level, is that the inputs have a very well-defined structure. So either if I'm using a REST API or a gRPC API, it has a very well-defined structure, and just throwing some random data at this will not be able to trigger or to execute this code at all. Yeah, so the second thing is, so we see this, obviously this code snippet contains an SQL injection vulnerability, because we're just executing an SQL statement based on some user input without any sanitization at all. But the question is, how can we detect that when executing this statement, we actually can trigger a bug, an SQL injection? So one idea would be, okay, we can just try with some built-in attack scenarios that that could lead to an SQL injection. But in many cases, also these statements are sort of protected. And then we can analyze the response of the application. But in many scenarios, these statements are sort of protected by try catch statements. So this will not reach out or will not leak into the response. So, and usually fuzzing so far has been sort of used for memory unsafe languages like C and C++, where you have other types of error. But here we need ways to be able to detect these kind of OS vulnerabilities that are relevant or mostly relevant for web services. And yeah, the code is also usually full of these checks. So it's not only that the code has a specific structure, but the concrete request that you need to send into the application might fulfill some further conditions or further requirements in order to basically trigger interesting code. So, and in this case, we see that the username is being compared to Larry, and only if this is fulfilled, we will be able to execute the SQL statement. So just to put it short, a fuzz or a testing tool that in order for it to trigger this SQL injection vulnerability, it needs to provide an input that has respects sort of the structure of this endpoint. It has to have Larry as its username, and it has to find a way to check or to trigger the SQL injection vulnerability. So it's quite challenging. To make things even more difficult, so modern web applications or microservices, they have a microservices structure, meaning they have a complex deployment. So here we see that an example also of web code is a Docker Compose file where it starts or deploys multiple services. And it's in real world application, this can get more complex. So we see more complex deployments that are being done in a Kubernetes cluster, for example, which makes things challenging. So having looked at these basically four challenges, what can we do about them? So we had the first challenge is what we have structure inputs, and what we can do is that we can sort of teach the fuzzer to generate inputs that respect a certain structure. And so what we see here is we see the usual workflow of what we've seen before of feedback-based fuzzing. And what we mean with that is that usually for a web application, you have an interface definition. So you have maybe your Open API or Swagger definition that specifies the structure of the endpoint and what inputs they accept. And what we do is that you can just take this information, this interface definition, and then build a web grammar based on it. And basically what this would be a layer on top of the generic fuzzing approach, where we use the interface definition of the interface structure in order to still generate generate random inputs or random requests, but that these requests should respect a certain grammar. And then with this, we make sure that it has two advantages. First, we make sure that any inputs that we generate actually is accepted by the application. And second, since we have this open API definition, we don't have to write fuzz tests when we do a system level fuzzing. So if I want to test my entire web application, I just use the Swagger definition as a starting point. Yeah, so the second problem, which is the bug detection capabilities, because how do we know if we reach an SQL injection? So one thing that we can do is, and that we do also in Jazzer. So again, if you have a look at the Jazzer repository, you will find some of the bug detectors that we have that we open source, and SQL injection is actually one of them. And so these and Jazzer has a hooking framework, basically, where you can define your own bug detectors. Then this would enable you to intercept certain events during the execution, and then perform your checks there. And I encourage you to have a look also at the blog post that we recently released about how to write bug detectors for Java or for Jazzer. And yeah, so the idea would be just to intercept certain or interesting methods and then perform some runtime checks. And so we'll see just in 2 slides how does it look like. So the SQL injection bug detectors basically checks if we can sort of manage that the fuzzer input actually lands in the SQL statement, because in this way you have achieved that your fuzzing generated input actually lands in the SQL statement. And what we do is we check, is the statement actually valid, and if executing the statement results in an SQL exception, and meaning that we have a valid statement that results in an SQL injection. So this is highly likely that we've managed. So the fuzzer input has managed to make it to the SQL statement. So we'll see an example in just a few slides. And you've seen these checks, and as we've seen in the first example that I show with Jazzer, is that string compares for Jazzer are really easy to crack, and even more complex ones are easier. And yeah, so this is sort of solved by coverage guided fuzzing or feedback based fuzzing, sort of out of the box. Yes. And so let's have a look at how this would look like in sort of in action. So we'll have this the example of web code, where basically this is the code of the endpoint, and Jazzer, or we would just start because we know we have the Swagger definition, and for Spring Boot we can just also extract this information automatically. So the fuzzer would just try to generate this post request, because it knows that it has a password and a username. For now, it will just generate random foo and bar. And this, of course, would not be able to pass this if statement. But while executing this, the fuzzer would get the feedback that part of the input is being compared to Larry. And so in one of the future mutations that it does, it will just use Larry as a username. And now you are able to pass by this check and actually execute the and actually execute the SQL statement. And so further, fuzzer would just do further mutations. And now what we, with this input, so the fuzzer would just also try to guide, also they will just try to find inputs that triggers this SQL exception. So, and what means that we actually triggered the execution of a valid SQL statement that actually causes an SQL exception. And this means that it's highly likely that this is because the fuzzer input, or the fuzzer generated input has landed, so let me unsanitized in the SQL query. And yeah, so this way, also based on this feedback, the fuzzer we were able to just explore the interesting program states and trigger the vulnerability. Okay. So the third problem is that we had this issue that modern web applications have complex deployments. They are deployed in a Docker Compose or even a Kubernetes cluster, and so these different services, they don't live in the same process as we've seen with unit level fuzzing. So what we do now is what we can do here is each microservice, if it's written in Java, we can attach a Java agent, a fuzzing agent, but this can be done also for other languages. So if you have a Go or C++ application, we can do the same thing where we can instrument these applications and then we attach our native agent in these cases to them. And what this would mean is that this agent then performs or monitors the code coverage and the interesting behavior that's happening inside of each microservice. And these will then get reported to the main fuzzer, so that even if the services run in different processes, they communicate their feedback to the main fuzzer. And it's even possible that these services can be written in different languages. But so we have one service in Go, one is in Java, one is in C++. Each one can have their own agent that can communicate with the main fuzzer. So this way you would be able to also fuzz multi-language applications. Just final word about CI/CD integration. Yeah, so until now, I hope I was able to convince you that fuzzing on a unit level is really, really effective, and it can be used to fuzz a whole web application. But even fuzzing, regardless how effective it is, it can only be effective if it is continuously done, meaning if it's integrated into the CI/CD pipeline, meaning only this way you will be able to shift the burden of finding bugs to the left, and we can only guarantee short feedback cycles for the developers, so they can short feedback or instant feedback about the bugs that they find. So how the workflow would look like is that imagine you are working on a feature, you just push this feature and you create a merge request or the pull request. This would automatically then trigger fuzzing. You get the feedback that you have findings. You can have a look at the findings to see which vulnerabilities, which bugs have been found. And here you also again with fuzzing, as mentioned, because you get the concrete input, you get the stack trace. This would enable you to just quickly, after pushing your code, to know what happened wrong, and to have sort of the information that would enable you to know what went wrong, and even start in a debugger, and then just with this short feedback cycles, you can guarantee quick bug fixes. So just finally some closing thoughts. Yeah, of course, as I mentioned, Jether is completely open source, and so if you have any new bug classes that you would like to see a detector for, or if you have issues using Jazzer or ideas how to improve the usability, then you come talk to us. We will be happy to accept your pull requests or issues just to improve Jazzer. And also just what's coming next from our side as also we are working on a support for new languages. So JavaScript is an example that we will be open sourcing shortly in the coming weeks. So this is so fuzzing for the JavaScript. So for this will be also completely open source. And what's already open source is our command line interface CLI tool that would enable you to write for easier way to develop fuzz tests and integrate those into your project. So also I encourage you to have a look at. And there the goal would be to make writing fuzz tests as easy for developers as writing unit tests. And also many or focus on our side will be developing more bug detectors for memory safe languages. As we saw in the context of applications, we're interested in finding SQL injection, remote code executions, and stuff like that. So this is also will be a focus. So finally, some takeaways. I mentioned so the takeaways. So would be fuzzing can be integrated. It's very effective and can be integrated at any stage of development. It basically trades your expensive dev or engineering time with CPU time, which is cheap, so that the developers or engineers they focus on developing useful features for the users, and it's important or effective for both for memory safe and memory unsafe languages, and it's at most effective when done continuously, meaning when it's integrated into the development process or and into the CI/CD pipelines. And so what we hope to achieve with that is that we don't release bugs or software with bugs that fuzzing would have caught or would have been able to code. And yeah, with that, yeah, thank you for your attention. And if you have any questions, feel free to ask.